Hi, coming to the table of contents. Initially, we'll start with CCO introduction. We'll learn on the trade-off and certain prerequisites which is required to understand the CCO use cases. After which, we'll jump into the code flow of implementation of Mavericks CCO, the demo, and conclusion. The term CCO, that is coverage and capacity optimization, is very generic and covers a broad range of use cases. Many of the SON use cases defined by 3GPP are somehow related to CCOs efforts such as cell outage compensation, mobility load balancing, and interaction between home and micro InnoD. As defined by 3GPP, CCO use case is understood as an automatic cell planning in which the SON algorithm must find the optimum antenna and RF parameters for sectors that serve a certain area for a particular traffic situation. The optimum result should maximize the network throughput or capacity while also complying with a certain set of confidence level of service which is specified by the operator. The term coverage refers to the coverage of basic services or user services. Basic services includes the reception of DL control channels and setting up of SRBs or signaling radio bearers. User services refers to services such as speech, video telephony, and others, etc. The term capacity has various representations. There are several options for capacity: cell throughput, median user throughput, X percentile cell edge throughput, and number of users or UEs served, that too with a specific service or a bitrate requirement. Let us understand the pre existing solution. The traditional way was to find the problems by doing drive tests and using planning tools to find possible solutions. This requires an extensive data collections from the network, including statistics and measurements, such as extensive drive tests. Here, the CCO aims at discovering these issues, the capacity and coverage problems, automatically through measurements at the nodes and those reported by UEs. It minimizes human intervention and reduces the feedback delay. CCO's corrective actions comprises of changes in radio parameters such as antenna tilt and UL power control parameters. The deployment of picocells or coverage capacity enhancing features are also corrective actions that may be proposed by CCO to reach desired target. The CCO should not react to performance of individual users, but rather it has to compute the appropriate CCO based actions on long-term statistics. The expected outcome of CCOs are to provide continuous coverage, increased capacity of the system, interference reduction, controlled cell edge performance, savings on drive tests, minimized human intervention in network management and optimization tasks, and self-healing in case of equipment failures at E node Bs or G node Bs. There is a trade-off between coverage and capacity. So typically, increasing the coverage results in less spectral efficiency due to deteriorating signal power, resulting in less capacity. We cannot optimize both coverage and capacity at the same time. Therefore, there is a need to balance and manage this trade-off between the two. Let us look into the use case of isolated coverage enhancement or optimization. In this use case, the actual coverage area of an isolated island cell is smaller than the planned isolated island cell area. The area that is not covered in the planned cell area is the coverage hole that is needed to be detected and optimized by the coverage and capacity optimization function. Optimization of the coverage holes. Here there are two examples. One which is taken with IRAC coverage, one with only 5G coverage. In the first use case, the 3G and 4G provide radio coverage together with NGRAN. However, in the first deployment stage, NGRAN could be of unsuitable planning or error parameter settings will lead to certain coverage goals in some areas. In this scenario, there may be IRAT handovers and there may be too many IRAT handovers. The CCO should be able to detect these kind of problem coverage automatically based on the frequent IRAT handovers. And in the below mentioned another use case, there is no 3G or 4G coverage except NGRAN. In the first deployment stage of NGRAN, unsuitable planning or error parameters again with these settings will lead to uncontinuous coverage in some areas. This will lead to call drops, many call drops because of bad coverage. CCO should be able to detect this kind of problem on the network coverage automatically. Let us look into the next use case, that is to detect overshoot coverage and optimization of the same. In this case, the operators do a gradual network evolution using NRSL in a location with higher capacity need. The actual coverage is more than the planned coverage. The problem with too large coverage is that the planned capacity may not be reached. As such, it is important to keep the coverage in the planned area. This problem has to be automatically detected by CCO. Let us look into the next use case, which is self-healing. Due to various factors and issues which can occur in real time, the G0Bs can go down. CCO must detect the cell down at real time by recognizing lost connectivity to G0B or sectors of the cell and the lack of UV data. And CCO must intimate the surrounding cells to modify their parameters to provide the coverage to the cell area which is previously lost. And all this has to be done without human interaction. Also, after detecting the cell up, it must realign the parameters of the surrounding cells to normal or as they were before. Also, having sectorization in this scenario helps in defeating interference. Below, we have two examples. On the left hand side, we have a cluster of 7 omnidirectional cells with the center cell being marked in black, which is representing the cell down. Cells which are marked in red are chosen for antenna parameter modification. After modification, you can see in the right hand side, the lost cell coverage is being covered. Also, since it is omnidirectional antenna, it can increase the interference in the surrounding cells. Hence, if we have directional antenna, we can use the directional antenna to modify particular direction antenna of a sector which is immediate neighbor of the lost cell by reducing the interference. Finally, for the CCO to reach the capacity and coverage optimization targets, the parameters that are needed to be optimized by the CCO function is downlink transmit power, antenna tilt, and antenna azimuth degree. Let us carry on with the demo on coverage and capacity optimization of an rApp implementation in Maveric RADP.
Setting the Python path. Now I am executing the CCO example app. As you can see, initially it is checking the model status, yet model is not trained and it is waiting for 3 seconds, and after that it is going again over the loop, and after it is showing model training job complete. After that it is running simulation. I have already run the this CCO example app because it will take some time. So I'll show you the output result of it. This is the last time it run the simulation. Simulation will run n number of time. In the simulation we have cell IDs, Rx power DVM, longitude and latitude of the UE, mock UE ID and tick value. Mock UV ID, as you can see, it is continuously repeating 1 2 3 1 2 3. That is because in this case cross replica is true, as I shown in the flow diagram. After that, when the run method return the RF data frame, coverage data frame, we are printing that in the RF data frame. It is showing location X, location Y, that is the location of UE, and cell ID, and SNRDV, and RX RPDV DM value. It is showing for this location. From this cell we are getting the SNRDV value is 9.0065 and SNR value is minus 73.65. This is the best SNR or RX RPDV value we are getting for this location. Like this it is showing. In the coverage data frame, it is showing location X, location Y, and RXRP dBm value, SNR dB, and covered. It is telling area is whether area is covered or not, and it is also calculating soft weak coverage, soft over coverage, and the addition of this soft weak coverage and soft over coverage, we are calculating network coverage utility. In the CCO objective per approach, as you can see, when we are optimizing elevation degree of the cell, as you can clearly see, the value of CCO objective is increasing, getting better. Okay, initially it is when the elevation degree of all the cells are 12 degree. In that case, our CCO objective value is 376. When we have optimized the elevation degree, we have the CC objective value way better than initial one, as you can see, 414.07. In the opt per approach, we are storing all the elevation degree that we have tried. For the initial approach, we have all the cell have same elevation degree, 12 degree. After that we start changing the elevation degree. As you can see, this in the last we are getting the most optimizing elevation degree values.